Hello, 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 hello. I am live. I don't know if you can see me, but hopefully you can see me and hear me fine. Tonight is going to be a little bit of an informal live. I just decided to go on. I am finishing up some stuff and here I am. Here I am after the gym and you know, I'm not super dressed up or anything, but I figured we can chit chat for a little bit. I might have to put some lotion on because still haven't done that. Fixing my hair here a little bit. So I hope that I see many of you joining. If you're going to be joining, I will be also looking at the live over here to make sure all the settings are set. And I do hope to say hello to many of you tonight. And Snugglemoy! Hello, my lovely friend. How are you doing? How are you doing? Oh my gosh. How are you doing? I just opened up YouTube and they are saying 10 channel members in, way to go. Your community is growing. There's no stopping you now. Wow. Thank you everybody for becoming a member. Who became a member? How nice indeed. I am so excited. I'm so very excited. Snokamoi is saying, Buttercup, I'm great. Oh, very nice. So I'm going to start to look at the live on my other phone so I can see what is happening and share it accordingly. And I also want to go look at it on the YouTube live monitor to make sure that the settings are set. And I'm running some code and whatnot on my laptop, so I might be looking at this direction at some points because I need to be checking on something. How is everybody doing? If you're joining, please do say hi. Please do like, share, subscribe. Please do tell your sisters, tell your neighbors, tell your brothers about the channel. And I hope to see many of you joining. And I hope to say hi to you live right here, right now. We can catch up. We can go over some interesting topics in physics, cosmology, astronomy, and astrophysics. Thank you for liking. This is going to be about physics, cosmology, astronomy, and astrophysics. How are you? IHFD says hi. Hello, IHFD. Casper says, what is this about? Hello, Casper. GP7072 says, hello. Hello. Caleb Taylor says, hi. Do you love space? Yes, indeed I do. I love space and I love particles that are originating in space in various locations, especially astrophysical sites, and that come here and then bombard our planet and sometimes interact in various medium/media. And then depending on which particle, we can learn certain things and whatnot. Yes, I like space particles. I liked the video and subscribed. Oh, thank you so much, IHFD. Defajajay. Defajajay. Thank you for being here. I like the video. Thank you. Casper says the string effect. Caleb says you sound really nice. Oh, thank you. I am, brother. Little bit. Quite nice. So, let's see. Is my living? Is my monitor showing the live? Let me look over in this direction for 1 second, okay? So everybody, please do say hi. Please do stay on. Don't go anywhere. We are still here. And thank you. And wow, thank you for liking the live, everybody. Oh, thank you so much for the emojis and hearts. Oh my gosh. How very nice of you indeed. How very, very nice of you indeed. I was running some code for my work and it's kind of running in the background here, so I decided I can do a little bit of a live right now and do here. and answer any questions. So if you're new to this channel, I do hope, okay, what did I call this? I call this Physics Live. Yes, okay. Hi, Caleb. Thank you for saying hi. Hi. Hello, Joe Schmo. Joe the Schmo 5170 is saying hello, miss. How are you, my lovely friend? Like and subscribe. Like and subscribe, please, please. Thank you so much, everybody. I am so happy to see you. Indeed, I'm a little bit late, and so I might have missed a few people. In which case, sorry about that, and I hope that you see this later on under the live tab of the channel as a video upload later on. And you can always catch it there. Who is this? Let's see. Namaste, says AKP Ghost. Hello, Ghost. I arrived from a live stream about protesting in Portland. Hello, chat. Hello, Portland. Hello, chat. Hello, Task I2D. Are you a mom? I am a cat mother. Yes. I was holding a firework while it was lit and and it exploded my hand off. Oh my goodness gracious. Hello, Task. Hello, Karen Jackson. Hello, everybody. Indeed, hello, hello, hello. And hello, hello, hello. We are here, we are here, we are one, we are all. And we will be chatting and we will be catching up. And if you want to shout out, then now is the time. Slash really at any point, you can send a message or a comment on this chat. And generally speaking, if you're new to this channel, generally speaking, we talk about physics, cosmology, astronomy, astrophysics, these amazing topics, which are also my background. I have a specialization in these topics and yes, physics. And we also show kitty cats on this channel. So me and my family of kitty cats are sort of the host, basically the ghost and the host. Well, hopefully not ghost, but mostly just the host of this channel. And so we do welcome you immensely. Task is saying, damn. Hello, how are you, says Lily. Lily, how are you? Lily 660 or Lily. Lily 66 is saying, hello, how are you? How are you, Lily? I'm learning on YouTube, yes. So generally speaking, when I go live, there's a lot of questions. Lately, people have been asking a lot of very pertinent questions about various cosmological and basically mostly cosmology and astrophysics topics. So if you have some kind of question about physics, the universe, cosmology, then feel free to ask it in the chat. I'm from the Sultanate of Oman. Welcome, Oman. Oh yeah, I forgot to do my continents. Welcome, Asia. Welcome, Africa. Welcome, South America. Welcome, North America. Welcome, Europe. Welcome, Antarctica, my favorite. Welcome, who else? Do I have all the continents now? Africa, Asia, North America, South America, Europe, Antarctica, Australia. I completely forgot. I'm so sorry. Australia and New Zealand. I know those are two different countries, but there is the continent that contains the Australia and New Zealand and the Southern Ocean. Thank you and welcome to the Southern Ocean as well and its inhabitants. Some of the inhabitants of the Southern Ocean are quite large, is what I was told in Antarctica. Welcome, my friend, and this is the most beautiful like for you. Oh, thank you. Lily is the top fan right now. Oh my goodness gracious. Let me see. Top fan, Lily. Wow. Number 2 is Caleb. Number 3 is Snokomoy. Number 4 is Casper. What a nice name. Number 5 is the IFD. Number 6 is GP 7072. Number 7 is Karen Jackson. Number 8 is Girl. Number 9 is AKP. And number 10 is Joe Schmo. Everybody, thank you so much for joining and for supporting this live stream episode tonight. Would you send Baji to space if you had the chance to be the first cat? No, because I'm his mother. I'm quite protective and a helicopter parent. And helicopters cannot work in space. That's my cheeky answer, but also it is the reality. It is the true reality of the situation that my children are not allowed in space because I am a helicopter parent and helicopters don't work in space. So you are really nice. Your style is really, oh, your style is really beautiful. Oh, thank you so much. Well, how very kind of you. Yes, we can talk about black holes. Children equal to space. What do you mean? We can certainly talk about black holes if you'd like. Certainamente. So we can definitely do that. I may have to check on something right here. Give me 1 second. Okay, sorry about that. How's Baji? Baji is good. Actually, hi Gary. Hello, how are you, Gary? So actually, Baji, they had their vet appointment today. So we are actually kind of upset today. It's been an upsetting time because whenever the veterinarian doctor, is that how you say vet? Yeah, veterinarian. Whenever the person comes, that's their vet, we all get a little bit upset and traumatized. And so today has actually been a rather difficult day indeed. But let me talk about black holes. So Centauri star is closest. Proxima Centauri, yes. Premix, no. Proxima Centauri is the name that you're thinking of, I do believe. So now let me answer the question that somebody asked earlier about black holes. So really quickly, a black hole is a stellar remnant. Okay, so when stars die, because eventually they all do, because a little bit tidbit about stars is that they're nuclear physics powered. So they are burning, they are alight, they are starring, as in a star is a star, because it is doing nuclear physics in its belly. There is a nuclear reactor, quite literally, in the belly of a star, producing heavier elements from lighter elements. For example, our sun is producing helium from hydrogen, and that's what it does. And this nuclear power is, of course, good for us. It makes the star, star and give off light, heat, energy, and that's how we get our life energy and whatnot. Like we are able to sustain ourselves utilizing this energy from the sun. But also, this is what keeps the sun alive. So in order for the sun to be alive or other stars to be alive, it is extremely important to keep on burning and keep on doing this nuclear physics in the star's belly, because once it runs out of nuclear power, and there is a whole detail of why that would be, there are various processes and whatnot in which different elements are being made, and very quickly at some point what happens is the nuclear binding energy becomes quite stable. For, say, for example, iron, there are certain peaks in nuclear physics where once you've made that element, it's going to be hard to take that and make heavier elements. You need even more heat for that and more extreme conditions for that. So those are the reasons why at some point, depending on the star, you can hi Combat Sports, hi Gold Scully, hi Steven, hi Steven Spears, hello my friend. Depending on the star, you can run out of nuclear power, okay? And we won't get into too much detail of that because I'm already giving you probably a bit more than what you might be interested in immediately. But the thing is that this is all very important, okay? The details are very important. So when a star gets close to basically running out of its nuclear power, it will be in danger of collapsing, because there's really two main things going on in a star. It's gravitation, which is an attractive force. Gravitation makes matter clump, as in matter fall, um, or collapse upon itself, right? So pretty much, their food is falling. 1 second, please. So pretty much, without the nuclear power, a star which has a lot of mass would basically collapse upon itself. So this is what leads to a star's death. So what do we mean again by a star dying? Couple of things. It's run out of its nuclear power. And secondly, because of that, it's going to now collapse upon itself. Now, this collapse is not a very straightforward event. It does lead to something like an explosion, like someone mentioned just now. There is what we call a supernova associated with a star's death. There are various types of supernovae as well. We can get into that at some point as well. And we have talked about all of this pretty much on the channel at some point or other. But basically, now the star is going to kind of explode. There is a very sort of extreme event going on, and the process of which ultimately the star is dying, right? Now, once the star dies, remember the whole issue was that the nuclear power is done and it's going to collapse. So the gravitational collapse now leads to quite an extreme compression of the star's material. The material that is not already blown away. Because by the way, oftentimes a star's kind of outer layers are actually lost to the interstellar medium, to space. Space is what we all know and love, but sometimes, in fact, oftentimes during a supernova, a star's layers, outer layers especially, are basically goes like this everywhere into the interstellar medium or space. Straightforward, okay? And in fact, that gas that's ejected from a star and becomes basically part of the cosmos, if you will, that is actually also very important. That's how we are here. If stars didn't eject material into space, and then that material becomes all this gas, and then the gas becomes a nebula, and the nebula condensates at some point to become something like our solar system, then we wouldn't be here, okay? So very important part of a star dying is also the process that leads to us being here, okay? We are all stardust, but we would not be stardust if the star didn't die and give off this dust, right? Or the gas, lots of material actually gets ejected into space. So then all of this happens as part of that supernova and the explosion. But then what happens? Long after, pretty much, hi Crazy Sick Wine, hi Franke, hi Caleb, hi Gold Scully, how are you doing everybody? How art thou on this splendid night? Hi, I'm good, I'm here. How are you? Tell us something about your school and everything. So, now that we have done this dramatic explosion, all this stuff, at the end of the day, that dead star is alone and lonely, and it will collapse into some kind of object, right? Now, it's not always alone and lonely. I should take that back, because sometimes this object can actually be in a binary, right? You can actually have a binary of something and something else. It could actually have a companion, but this star has died. It will now collapse. Now comes the important part about what someone asked, which was they asked about the black hole. So now listen closely. Depending on the mass of the original star, the star, once it's dead, will collapse into one of three types of objects. There are really just three options for it to collapse into. And this object is made because of massive gravitational collapse and compression, where a much bigger object is being smooshed down into something much smaller, something much more compact. Smaller as in smaller volume. Okay? Much more smaller volume than the original star. And what are these three types of compact objects that a star can become upon its violent death? What are these three options? Number one, for the lowest mass stars, it will be a white dwarf, what we call a white dwarf, and we can go into details of that. Number two, the middle mass stars, as in more massive than the lowest mass, will become neutron stars. Neutron star is also a type of compact object that a star can become upon its death. It's got star in its name, but it is not a star, it's a dead star. Okay? It's not technically a star. Because it's a dead star, it's a compressed object. A pulsar, exactly, neutron stars often are also associated with pulsars. Pulsars were discovered and they were actually associated with neutron stars. So that's the second type. And then thirdly, the most massive stars originally will then, it froze. Did things freeze? The most massive star will compress down and collapse down into a black hole. Can people, is it working or not? Crazy Sick One is saying it froze, my dear, but is it really frozen? Hi, the bears. How are you? Okay, I think it's working. Oh, thank you, Ivan. Thank you for confirming. Hi, Greg. Hi, Nehilal Ahmed. Hi, Ivan. Ivan is saying, I'm great. Are you still in school? Hi, the bears. No, it's running. Thank you. Thank gosh. Well, Crazy Sick One, it might have frozen up for you. So the third type of collapse, which is associated with the most massive stars. So the most massive stars will have the most extreme collapse, the most extreme compression of all. And these basically collapse down into a black hole. So now, what is a black hole, right? Now, I just talked about what kind of makes a black hole, right? Originally, a black hole is nothing but a stellar remnant. So the leftover after a star has died is basically a stellar remnant, and there are stellar remnant options depending on the mass of the star. These are white dwarf, neutron stars, and black holes, where going from lowest to highest mass stars. So the highest mass stars will compress down and collapse down into a black hole. But sometimes, and we talked about this as well, sometimes a black hole, once it's been formed, can keep on eating more material. Basically, it is being fed by its surrounding materials, and it can basically get bigger and bigger and bigger over time into a supermassive black hole. So that's another way as well. So this is to answer the question that somebody asked, how black holes are formed. So I told you the fundamentals of a black hole, which is that it's a stellar remnant. It is associated with a star dying and massive gravitational collapse and massive gravitational compression. And depending on the extremeness of that collapse, you either get a white dwarf, neutron star, or black hole. And how extreme the collapse is really has to do with the mass of the original star, which is really quite elegant, that in astrophysics, a lot of things depend just on the mass of the star. If you know the mass of the star, if you find a way to know the mass of the star, you will actually learn a lot about the physics of that star. Now, there are always more details that are that we may want to probe beyond what I'm talking about. Like, for example, there are different nuclear physics processes that make the different types of elements in a star. And for that, there is more that's probably going on. But a lot of things quite literally can be sort of deduced from the mass of the star. Hi, Acacio. Buenas noches. Hi, Steven. Hi, Yuri. Hi, Yuri Chit Sung. Hi, Stroker. Okay, so that's the fundamental how black holes are made. And then also I wanted to mention about the supermassive black holes, which really happen because a black hole that's been made already is continuing to accrete a lot of material into it, continuing to eat a lot of material from its surroundings. Even our own galaxy and lots of other galaxies have a supermassive black hole at their centers. And these supermassive black holes are not just the ordinary kind of black hole, they are accreting, as in lots of material is falling in an accelerated like manner into this supermassive black hole at the galactic center, for example, of our own galaxy and as well as other galaxies. And upon, after centuries and millennia and millions of years, billions of years of that happening, the black hole eating material from its neighbors and surroundings, and material falling into that black hole in a violent manner. Like sometimes it's super duper accelerating as it's falling. And so, by the way, that is also, it also sets up that type of environment, also sets up a particle acceleration type of environment, lots of accretion, lots of acceleration. And it can also lead to a lot of radiation from all this matter that's infalling into the supermassive black hole. Okay, so actually, as much as a black hole is very dark, obviously, the classical definition of a black hole is that there even light does not escape the black hole. But around the black hole can sometimes be very bright. This is also something I wanted to mention in while we are talking about black holes, is because it's not bright because of the black hole directly, but it's because of the surrounding material that is falling into the black hole. And as it's falling, it's accelerating and giving, and it's not just falling in a chill way, it's falling in a very non-chill way. And it can accelerate, it can give off a lot of radiation in all different kinds of wavelengths. And that's what can make the surrounding of a black hole bright in different wavelengths, okay? So I'm mentioning this because this is more of a supermassive black hole situation, which of course our own galaxy has at its center. Sagittarius A star is the name of that supermassive black hole at the center of my galaxy, at the center of our galaxy. So those are sort of that's my little spiel on black holes for you and how they're formed, depending on just a normal black hole or a supermassive black hole, okay? You seem extremely chill. Hi, Lewis. Condensed matter systems and quantum computing is proving rather difficult. I can't speak a lot of words without taking a breath, it's true. Hi, Acacio. Condensed matter systems and quantum computing is proving rather difficult. You seem extremely chill. Didn't know that, not gonna lie. Didn't know what? We were just talking about black holes, groove toot. She's as cool as they come, but Dree could also be very wild. Hi, Steven. Wild in what way? Whew. There's my breath. Now we will do deep breathing session before the next question comes. Before we address the next question. You're too much. Okay. Also, let me I think somebody asked about the size of a black hole. So let me utilize this book and give you the exact number. So this is an astrophysics book, Foundations of Astrophysics by Barbara Bryden, Bradley M. Peterson, my favorite. So now let me tell you the size of Sagittarius A star, okay? Which is a supermassive black hole. So I understand that that is not going to be representative of normal black holes, but let's get a few extremes. I've seen you get very excited and joyful. It's another part I love about you. I do get very excited and joyful. Hi, where's the QR code to donate? Well, I have a PayPal link in my bio, and there's also a button probably to do the super chat here on the live. Thank you everybody so much for all your support, likes, shares, subscribes, super chats, super whatever else is. I think there's buttons on the live where you can do that. Emojis, hearts. If you really want to donate to my PayPal, there's a PayPal link in my bio. I have seen you get very excited. Yes, I have had a few drinks tonight. You've had a few drinks tonight on a Monday night. Are we celebrating something? Is it your birthday? It is my birthday week. This week is my birthday week. So I think on Thursday night, I will probably do a birthday special. Lewis is saying, subbed, you're cool, my girl. Oh, thank you. But yeah, feel free. Feel free to do a super chat if you like. Feel free indeed. Okay, so I wanted to look up. I have to go to bed, says Gold Scully. No, just to relieve stress. Aw. How is everything going recently for you, Crazy Sick Wine? Will you be 36? How could you? Do I look 36 to you? Okay. All right. Sagittarius A star, according to this book. Oh, Combat Sports, I read that you're in Worcester. Are you enjoying the Worcester? Where the roosters are? I reached my hotel. I will sleep listening to you. You look 36 million years old. I mean, we are at least 4 billion years old. So, you told me you were 35. I thought, my apologies, I meant 26. I didn't tell you I'm 35. I mean, you're close, but I'm not yet 35. So, there is that. As far as I know, I'm not 35 yet. But what we'll say is I'm 25, but with a few years of experience. This is my new way to say things, okay? I am 25 with a few years of experience. So don't ask anything more detailed than that. Observations by the Chandra X-ray Observatory revealed that Sagittarius A star, this is the black hole or the supermassive black hole at the center of our own galaxy, is an X-ray source as well as a radio source. So remember how I was mentioning that around the supermassive black hole can be quite bright? This is definitely the case for our own supermassive black hole because of all the infalling material into the black hole. The X-ray emission from Sagittarius A star varies significantly on timescales of less than 1 hour. This is important, revealing that the majority of its X-ray emission must come from a region less than 1 light-hour across. So that is sort of the length scale of Sagittarius A star, which is a very massive, supermassive black hole. So all this action with the X-ray stuff is happening from a region that is less than 1 light-hour across, which is 7 astronomical units, where an astronomical unit is the distance between the sun and the earth. So now there's some more information here. The leading hypothesis is that Sagittarius A star is a supermassive black hole that is accreting gas. A supermassive black hole is a black hole larger than what would result from a massive star collapse alone. So this is, again, what I was saying. A massive star collapse alone will not make a supermassive black hole. It's that the black hole has been made and it has continued to eat more stuff is why it becomes a supermassive black hole. Okay? So then, cutting to the chase here, somebody asked about the size, right? So, Sagittarius, is it giving me, let me just look it up on Google. So, our solar system, so the distance between us and the sun is 1 astronomical unit. And the X-ray emission business is happening from a region that is 7 astronomical units across. So, but also remember that we're talking about a supermassive black hole. Okay? So, it can be very much more larger. Okay? Let's see what NASA jet propulsion. So, by the way, all this deductions about the size of Sagittarius A star depends on the observations of the X-ray and the radio and on all of that stuff. Like, once we kind of know all those other things that are going on around the supermassive black hole, we kind of estimate the size of Sagittarius A star, okay? So it's going to be sort of an approximation, which I'm going to read out from here, but hang in there. So this is from the Jet Propulsion Lab, which is a part of NASA. So this article is saying that, let's see, what is the approximation? Do they have an approximation of the size? This is a cool website, as always. Okay, so the distance from the center of Sagittarius A star to its event horizon. So it's a black hole, it has an event horizon. So event horizon means you can go up to the event horizon. I mean, I wouldn't really recommend it, but you can go up to the event horizon, but any further than the event horizon and you'll fall into the black hole, never to return. So pretty much, actually, the other thing I should mention is that because it's a supermassive black hole, you can actually go, I wouldn't go too close, But actually, from from some distance away, obviously outside of the event horizon of the black hole, the tidal forces felt by somebody because of Sagittarius A star would actually be kind of small, because tidal forces depend on the mass of the black hole as well as its Schwarzschild radius to the 3 as in cubed, and Schwarzschild radius depends on the mass of the black hole. So because of that thing being in the denominator, actually the tidal forces would be quite small. And the black holes that are much more dangerous in terms of how much more spaghettification of somebody would happen near them are actually the smaller black holes, believe it or not. So smaller black holes are actually more dangerous than bigger black holes in terms of the tidal forces that you would feel. But okay. The distance from the center of Sagittarius A star to its event horizon, a measurement known as the Schwarzschild radius. So this is called the Schwarzschild radius, which is, of course, can be solved for a black hole once you set the escape velocity from the black hole to the speed of light. So in the case of Sagittarius A star, which is a very big black hole, it's enormous at 7 million miles. So 12 million kilometers, or 0.08 astronomical units. So Sagittarius A star's radius is 0.08 astronomical units, where 1 astronomical unit is the distance between the sun and Earth. Okay? Or in other words, it's 7 million miles, or 12 million kilometers. But that is the radius of Sagittarius A star, which is a supermassive black hole at the center of our own galaxy. Acacio! Oh my gosh, Acacio has done a super chat. Happy birthday. Happy birthday, my dear and charismatic teacher. May all your aspirations and projects be realized in your life. Oh, thank you so much. I liked and hearted your message, Acacio. Thank you so very much. Let me continue and then I'll thank you more. So I just want to point out, whoever asked about how big the black holes are. Black holes, the sizes are diverse. I'm giving you an example of a black hole right now, which is a very massive one. It's a very extremely big one. Okay, so an extremely big one, the extremely big one is this Sagittarius A star, which is of course very pertinent to us because it's in our own galaxy. That one is 7 million miles in radius. But there could be black holes that are as tiny in radius as several kilometers. It all depends on the mass. So actually, here's a little exercise for you. You could even be a black hole. You could even be a black hole. Anything with a mass actually can be a black hole. It just depends on compression. So on the higher end of things, a black hole, supermassive black hole, can be as big as this 7 million miles radius number. But guess what? Depending on your mass and depending on the Schwarzschild radius of that mass of black hole, your radius could be extremely tiny. Is it your birthday? Funny, my birthday is October 12th. Your birthday is October 12th? Happy belated birthday. It was yesterday? I ate a lot of food yesterday to celebrate, apparently, you. My birthday is October 17th. It's on Fry. It's on this Friday of this week. October 17th is my birthday. And I will be going live probably as my birthday becomes my birthday. So your mass is 185 pounds. Okay, perfect. Great. So now let us find your Schwarzschild radius. Should we just ask ChatGPT? Because I don't want to do the math right now, but I'll give you your formula. I'll give you your formula. ChatGPT. So the Schwarzschild radius, isn't it so lovely and interesting and amazing? The Schwarzschild radius of a black hole simply depends on the mass of the black hole. Simply by setting the escape velocity from the black hole in classical physics, utilizing relativity, to the speed of light. So as long as the speed of light from you, or the escape velocity from Ivan, as long as Ivan is a mass from whom the escape velocity is the speed of light, then we can solve for the Schwarzschild radius of U, which will be your black hole radius. Okay? Hello, Sebastian. So now I've told you that your Schwarzschild radius depends on your mass. And so now we will actually calculate it using ChatGPT, okay? Excuse me for using ChatGPT. I just want to do the calculation quickly. And I will say that the formula, and I will make sure that ChatGPT uses the right formula. It is, I do believe, but please double check. It is 2gm over c squared. So where g is the gravitational constant, m is your mass, the black hole's mass, over c squared. So let us use ChatGPT. ChatGPT, Ivan, and see, you gave me your mass in pounds, right? ChatGPT will hopefully be smart enough to convert that to kilograms. Ivan weighs 185 pounds. Calculate his Schwarzschild radius. Literally, it's using the point of the event horizon as its point of reference. Yeah, so the black hole center to the event horizon is the Schwarzschild radius. Yes. So in other words, the singularity, there's a singularity inside the black hole where the gravitational field is very extreme. That point to the Schwarzschild radius is the event horizon. The event horizon is basically a sphere of the same radius as the Schwarzschild radius of the black hole. And how you solve for the Schwarzschild radius is by saying, hey, here's this gravitational field because of this massive object of mass m, and I'm going to set it so that the escape velocity from this thing will be the speed of light, which is another way of saying that even light cannot escape the black hole. So then you simply solve for the radius at which that happens, and then you get your Schwarzschild radius, okay? So anything can be a black hole if you compress it enough. That's the biggest thing. So now think of it, right? So ChatGPT is working on that. So now, and when it finishes, I'll make sure that it use the right formula. Where is it? Oh, here it is. I have so many windows. I have too many windows open. So I can't even, you know what I mean? I can't even find it. Hopefully I'll find it. But anything with a mass, if you squeeze it enough, if you compress it enough, will become a black hole. But some things, it's more practical for them to become a black hole than Ivan. Ivan's mass is quite small in the end. We will see your Schwarzschild radius, and my guess would be that it is a very tiny, little bit unattainable radius. Now, we could compress you enough to that point where you would become a black hole, but it would be pretty tough. Whereas when a star, which is a much, much more massive object, naturally compresses, nature compresses it because of its gravitational collapse when it's dying. For a star, it's actually not so impractical. It's quite practical depending on how big the star is in mass to become a black hole. So this is the elegance of a black hole situation, is that, isn't it so lovely that if your mass is big enough and you compress that, it's not impractical to become a black hole. And they were not sure, like when the theory of the black hole, black holes were theorized before they were actually discovered in the wild. So they had solved general relativity for black holes earlier. This guy Schwarzschild, he's the one who did it as well. He solved the equations exactly for the black hole, and it was all great. But they did not expect that such a thing could really actually exist in nature. But then they actually got a lot of encouragement once they started to find neutron stars in nature, because they're like, wow, if something, because neutron stars radius is like 10 kilometers, literally. A neutron star is the size of Manhattan. It's very tiny, right? A neutron star is like 10, 12 kilometers in radius. So when they found massive stars compressed down to the level of a neutron star, and the first neutron stars were discovered, they actually got kind of excited that maybe black holes are real too. And sure enough, then we discovered black holes and whatnot. And now they're accepted, of course. But the theory for black holes, the equations for black holes existed long before they were started to we started to discover them. Now it's a little bit maybe difficult to discover black holes because until you start discovering them and you kind of see, oh, like around a black hole can be kind of bright because of the stuff that's falling into the black hole. But sometimes black holes are, because they're black, right? Like they're dark. In that sense, that they can be kind of tough to detect as well. You'd really have to look at the gravitational effect of one and see what's going on around it. Sometimes that's the telltale sign of a black hole, because it's really what's happening around it because of its gravitational effects that you really see one. But you might not be able to see one because it's dark. It's black. So because of reasons like that, they didn't discover black holes first. They actually discovered neutron stars first, as far as I understand. So but I think that the science of black holes is very elegant because you directly take general relativistic equations and you solve them very nicely, elegantly, and exactly for black holes because of the whole escape velocity, being able to set that equal to the speed of light. And that gives you an elegant, nice equation for the Schwarzschild radius of a black hole, which is 2gm over c squared, like I was saying. And whatnot. And so all of this basically gives you this classical relativistic theory and equations for a black hole. So now ChatGPT has finished. Mass 185 pounds, that is around 83.91 kilograms according to ChatGPT. Schwarzschild radius is simply given by 2gm over c squared, where g is the gravitational constant, m is your mass, and c is the speed of light. When we plug it in, we get, for Ivan's black hole radius, as in if Ivan was a sphere, if Ivan is approximated by a sphere, which I understand you're not probably perfectly a sphere, but in case you are, if you were, we can just approximate you as a sphere. And if we compressed you down to this radius, you would become a black hole. What is that radius? It's a very tiny one. Are you ready? So Ivan's black hole radius is 1.25 times 10 to the negative 25 meters. Once again, 1.25 times 10 to the negative 25 meters. So that is quite small. Why do I say that it's quite small? Hi, 123. Hi, Mr. Bates. Please do like, share, subscribe, guys, by the way. Why do I say that is small? Because negative 25, wow, 10 to the minus negative 25 is very small because, if I'm not mistaken, the nucleus of an atom is around 10 to the minus 15, I want to say. Let me Google it and make sure. Size of nucleus. Yes, femtometers. So I was right. The size of an atomic nucleus ranges from, basically it's the order of femtometers. Femtometer is 10 to the minus 15. Femto, FM, right? Very tiny. So the nucleus is as small as 10 to the minus 15. So if Ivan were to become 10 orders of magnitude smaller than the nucleus of an atom, like the nucleus of a small atom, I mean, like not even a big, not even a, because I guess the hydrogen nucleus, which is just the one proton, is like 1.6 femtometers, okay? Let's just call it 1 femtometers. So 10 to the minus 15 is the nucleus of hydrogen. If you became 10 orders of magnitude smaller than that, then you would become a black hole, okay? So I just wanted to make the point that anything with mass has the potential to become a black hole, indeed. So don't feel left out. If you want to become a black hole, you can. You would just have to be compressed a lot. Anything with enough compression can become a black hole. But where is that more practical? Natural for stars. For certain stars that are bigger. By the way, Ivan, don't feel bad. Even our sun is not going to become a black hole. The sun is pretty big, quite a bit bigger than Ivan. But even our sun will actually become just a white dwarf when it dies. So don't be disheartened. If you want it to be a black hole, you can. It's just going to be a little tough. We need the technology to compress you to 10 to the minus 25 meters. But lots of stars that are much, much bigger than the sun can naturally collapse down to that level where they, depending on their mass, would become a black hole, because the black hole radius or the Schwarzschild radius goes as 2gm over c squared, where the m is in the numerator. So you can imagine that the bigger mass black holes have bigger radius. So this is actually why, by the way, because the radius can be really big for a more massive black hole, so that's why the event horizon is much farther away from like the crazy gravitational field point of the black hole. And because of that, in the Schwarzschild classical way, the tidal forces on a person would actually be much gentler outside a bigger black hole, like a supermassive black hole. Hi, Adam. Adam Dolson. Oh my gosh, my friend from Canada. Am I right? When is your birthday? October 17. Free black hole for everyone after I become. Hi, Meow. Adam Dolson is here. Hi, Adam. How are you doing? Oh my gosh, that's right. The Canadian Thanksgiving. I will type my birthday since combat sports cannot see me. It's October 17, combat sports. October 17. Okay, so next we will talk about, okay, yeah. Let me finish that thought. Maybe I already did. Let me just say it again. The tidal forces on a person, like if you have heard of like spaghettification of a person near a black hole, or actually anything can be spaghettified depending on, right, what's going on. The tidal forces would be gentler outside a bigger mass black hole. And this has to do with its torsional radius being bigger as well. Okay? So anyway, hopefully that helped. Hopefully that helped with people's black hole questions. Are you from India? I am originally from India. Yes, indeed. And I also would like to say, I see one more. I see another question. Also, I want to say, thank you, Acacio. She's a Bollywood actress. I'm a Bollywood actress. Acacio, thank you so much for the super chat. I was in the middle of a thought, but now I want to thank you once again. Acacio said, happy birthday, my dear and charismatic teacher. Aw. May all your aspirations and projects be realized. Thank you, Acacio. I will go live again before my birthday / on my birthday. So hope to see you again. Hope to see everybody then. But it is this week. I celebrate my birthday for like 2 months. And we are now in the week of my birthday. So I am very happy indeed and feeling very festive with your message. Thank you very much. Muchas gracias, Acacio, my friend. Thank you. Okay. And Combat Sports is here. And his birthday was yesterday. So let's all say happy birthday to Combat. Happy birthday to Combat Sports, which was yesterday. Meowgesh is saying, you're from India? Okay, how nice. Okay, so somebody asked about, thank you, now I see you. Oh, you can see me, okay. So, ooh, I have 17 people and 34 likes. Oh my gosh. A multiple of 17. Oh, a multiple of 17 is here. And Adam Dolson, 252, has done, I guess you're a Libra, has done a super chat. Thank you, Adam. Thank you, the great nation of Canada. Wow, let me like and heart that. Goodness gracious me, Adam Dolson from Canada. Happy birthday in advance, ma'am. I guess you're a Libra. I am a Libra. Can you tell from my extreme charismas? And Bollywood acting? You are beautiful. Thank you. Happy birthday in advance. Thank you, Meowgesh. Sampath is saying Paduko Poyi. Paduko Poyi to you as well. Oh my gosh, thank you, Adam. I really appreciate it. Thank you, Akasu. I really appreciate it. Going to my sister's house, and any tips and tricks to sneakily steal food from the fridge and put it in my backpack? I find it problematic that the food in her fridge isn't in my fridge. Oh my gosh. No TK is asking for stealing tips. Anyone help? Anyone wants to help about that? Happy belated birthday to Combat Sports. New England accent. How old are you turning, says Beamer. Beamer, are you asking combat sports? Let's see what combat sports has to say about how old he's turning, and then we'll talk about me. I was saying earlier that I'm 25 with a few years of experience. I'm 25 with a few years of experience. The physics of thievery. I was thinking to cut the power cord. Well, isn't that how things are gonna go? Oh, go bad. Hi, Aaron. Okay, so somebody had asked, so everybody please do continue your cheerful banter. I'm really loving it and really appreciate everybody who is here and talking and chatting and commenting and sending these wonderful messages and supports and super chats and regular chats, and everything is most appreciated. Let me try to answer the question about the neutrons in a neutron star. So somebody had asked about the neutrons in a neutron star. So let's see, what I'd like you to kind of picture with the neutrons in a neutron star is that remember how a star, if we have so go kind of a little bit backwards. If we have a neutron star, it means that the star has died. If the star has died, it means is there a subparticle of quarks? Not that I know of. I believe that a quark is a fundamental particle, so I don't know if that, let me think about that. Yes, a quark, as far as I know, is a fundamental particle, so I know not of any further breakdown of a quark. Protons and neutrons break down into quarks. So yeah, speaking of which, this neutron star question, right? Being neutrons are ultimately quarks, right? So you might even think of the neutron star as a quark soup or very compressed, basically, state of these neutrons, right? So I don't really want to call it a kind of a quark soup. Like the neutron star neutrons are basically one big giant neutron. Like they're so close together that they act like one big giant neutron. The neutrons are indistinguishable from each other. But let's come to where these neutrons are really coming from. So neutron star means the star has died. If the star has died, that means that it ran out of nuclear power. Why did it run out of nuclear power? It probably made, and remember that neutron stars also come from stars that are pretty massive, not as massive as the ones that would make black holes upon death, but pretty massive. And we can get this exact ranges of mass here as well from the book. But these massive stars will generally have an iron core in their belly. Like they have taken all the lighter elements and made at least up to iron, okay? And they've gone through some explosive, disastrous supernova, etc., etc. But basically, they have made some pretty stable, like heavy elements. And once you've kind of exhausted your material and converted all the lighter elements to heavier elements to a certain extent, you basically have less and less fuel to make the heavier elements out of. Or in other words, there might be things to make the bigger elements out of, but it requires more heat, more energy, more pressure, more extreme conditions. And if the other way is sort of winning, where the gravitational collapse is sort of kind of starting to happen, blah, 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 you can basically start to get into this supernova stage and then you blow away. Remember, for these types of supernova, generally you've lost a lot of material to the cosmos as a ejection, basically. Like the explosion makes things kind of just spew everywhere, get ejected everywhere. out into the interstellar medium. So you also lose a lot of the gas that way. And then what is remaining at the end is literally the stuff that has compressed down, collapsed down. And so they're neutrons, because basically at that point, like you probably did in a star like that, the process that made the heavier elements, there's this process called neutron capture. You basically need to be doing that in order to make the heavier elements. Like after a point, if you don't add neutrons to the nucleus, you're not going to get the heavier and heavier elements. So anyway, basically part of it, I believe, is the stuff that it was making, and the second part is it's really the stuff of the star, but so compressed that it's acting like one thing. You can't even distinguish the elements anymore, the protons, the neutrons anymore, like that. But let's see what this has to say. That's sort of my explanation, but let's see what the book is saying. Quark pudding. Exactly. It's kind of like a quark pudding at that point. Hey, how are you? You are very beautiful. Is there such a thing as a proton star? There is not. So I'm thinking about this question. Partly, so partly the issue also, I believe, is that a proton, you can make a neutron out of you can basically make a neutron. There's nuclear physics reactions that can make a neutron out of a proton. So basically, I believe like the protons would like repel each other, and at those scales it's probably turning into neutrons, and the neutrons are neutral, and like it might, so let me double check with the book, but it might have some balance of like the electromagnetic force as well as the strong nuclear force, because basically if you kind of break through the electromagnetic force, exactly, then you are actually, the strong nuclear force will be the one that is keeping things together. So yeah, I think it's because the protons and electrons would combine to make neutrons, is sort of another reason. Hi, SSMW. They come together. Yeah. That's what I think. But I would like to just explicitly read that somewhere from the book so that I'm sure about it. You know what I mean? I think protons and electrons can combine to make the neutron, especially because under those conditions, why not? Like all kinds of crazy things are happening. So this can happen as well. And the protons would repel each other. But then neutrons are neutral. So really the only problem would be strong nuclear force. But because of the compression, and also, by the way, because of the neutrons also will not get any closer. Oh, this is the other thing. So the neutrons will not get any closer after a point. They get close, but they will not get any closer after a point because of neutron degeneracy pressure. This is definitely in the book. Because of neutron degeneracy pressure. Guess what? In a black hole, I believe you break through even that. Basically, even that neutron degeneracy pressure would be, what's the word, not obeyed or something in the case of even more extreme gravitational collapse, because neutron star is not the most extreme case. But basically, neutrons have certain rules where they can come close together because of this gravitational collapse and compression, but you can't get them any closer. Already they're very close. In a neutron star, the neutrons are so close, they act like one big neutron. You can't distinguish between the neutrons anymore. But they kind of flow like a neutron pudding or soup or something. But basically, you still have some radius of the neutron star, which is around like 10, 11, 12 kilometers. So what is that radius, right? Why is the neutron star being held at that radius? It's because of the neutron degeneracy pressure. So that phenomena. The same thing, which is the electron degeneracy pressure in the case of the white dwarf, basically. So, hi, Andre. They come together. Mr. Bates is saying you're right. Thank you. Hopefully that made sense. Andrew is saying hi from Australia. What's happening, Neil deGrasse? Yes, I am like Neil deGrasse, but cuter. Andrew is saying sounds interesting. Thank you. I mean, Neil deGrasse is great. Great voice. Great voice of that guy. So the stars that have initial mass greater than 7 solar masses will become that's a great question. So lots of squeezing in both neutron stars and black holes. The thing to note about the neutron star is that something is keeping it at a radius of 10, 11, 12 kilometers. There is a neutron star radius. And that thing is neutron degeneracy pressure. The gravitational collapse of a neutron star is not so extreme that then you don't even obey that. I do believe that in black holes, gravitation has won at all cost. All these things that should be obeyed are now not obeyed. The only thing that is obeyed is gravitational collapse. And so the black hole radius truly can be whatever number, depending on that thing I was saying, the 2gm over c squared, because of the escape velocity being set to speed of light. But actually that thing, so let's talk about it. The escape velocity being set to the speed of light is the classical relativistic approach for black holes. As far as quantum effects of a black hole, that's a different matter, right? So as far as a good approximation for a black hole, especially say like doing some kind of like problem solving with black holes, I think it's generally good enough to say that a black hole, if it can be approximated by a Schwarzschild black hole, you can do that thing. But that Schwarzschild radius equation and the classical relativistic equation being solved, setting the escape velocity to speed of light, that's the classical relativistic. That does not take into account quantum mechanics, okay? So any sort of more particle-y question you have about black holes would have to be kind of beyond that. And we do know that there are quantum effects of black holes because that's how they can have a temperature, etc., etc. Yes, the laws of physics collapse due to gravity becoming a mathematical nightmare. Exactly, and that is why we have a singularity at a black hole. The black hole is not a convenient object as far as the mathematics goes. There is a singularity inside a black hole because of everything collapsing, too much gravitation, and the physics just goes to becomes sort of undefined. So this is, by the way, a deficiency of general relativity. General relativity produces a singularity inside a black hole. There's two singularities that we know of, one inside a black hole and one at the Big Bang. So the fact that general relativity produces a singularity at a black hole and also at the Big Bang is considered to be a flaw of general relativity. General relativity is a very successful theory, has been proved in many ways, lots of good evidence, lots of good stuff coming out of it. But this right here, what we have hit upon, is actually a flaw of the theory because we cannot explain the physics and the math breaks down inside of a black hole. Okay? So, yeah, so there's that. But yeah, so I was right. Sorry. I forgot a little bit, but then I started saying stuff. But I'm seeing it in the book now about the proton electron thing becoming neutrons for a neutron star. So let me read that part. I said it already, but this is the more official text. So, for example, I believe even Betelgeuse, right? Even Betelgeuse, when it dies, I believe even Betelgeuse will probably become a neutron star when it dies. Just double check that. Somebody can Google it. But Betelgeuse, as you know, is really due for a supernova. And I believe it's big enough where when it will die, it should probably become a neutron star. So anyway, the central iron core of such a star, the one that will become a neutron star, is very dense, okay? Thousands of tons per cubic centimeter is what we're talking about here. And it's supported by degenerate electron pressure. The iron core continues to grow in size as the silicon fusing shell eats its way outward in this supergiant. So we're talking about the insides of this kind of star. When the iron core reaches the Chandrasekhar mass, by the way, this is a Chandrasekhar mass is around 1.4 solar masses, which is also the mass of a white dwarf. Okay, because guess what? All these like masses and radii and whatnot, they're all kind of linked. You can only, and why are they linked and what is driving them? Some kind of physics is driving the size of something, right? If you're big enough, or if you're not big enough, you can only be collapsed so much before some other physics will kick in, and that physics will stop you from collapsing too much. And so this electron degeneracy pressure is another thing where electrons cannot be squeezed further. They're too close to each other anyways, they hate it, and you cannot compress them more, which is the case in the white dwarfs. But with neutron stars, let's keep going, because neutron stars' core itself can be the size of what would be the Chandrasekhar mass, which is 1.4 solar masses. So literally more than our sun's mass can be just the core. Okay, so literally more than our sun's mass can be the mass of just the inside, just the core, like the iron core of a massive star, which is going to become a neutron star later on, can just be that. Just that part is more than the size of our sun. Okay, in mass. When the iron core reaches the Chandrasekhar mass, which happens to be 1.4 solar masses, it is no longer adequately supported by the relativistic degenerate electrons, and it starts to collapse very rapidly. So now you're breaking the physics of electron degeneracy pressure. Gravitation is so strong for this massive star, it does not care about electron degeneracy pressure. Electrons don't like being close to each other. After a point, I don't care, says gravity, for this type of for this type of core. The collapse time at the high density of a degenerate core is less than 1/10 of a second. As the density of the collapsing iron core rises, protons and free electrons, so there's protons, free electrons, start to combine to form neutrons. So this is what I was thinking happens earlier, and it does happen. So protons plus electron would give a neutron, neutron plus a neutrino. That's a pretty common nuclear reaction, actually. You get a neutrino out of most things. Most nuclear physics things happen, and you get a neutrino out of it. One side effect of the collapse is thus a huge burst of electron neutrinos. So this electron neutrino will come out of this process of the proton plus the electron becoming a neutron. A Chandrasekhar mass of iron contains around 10 to the 57 protons. So around 10 to the 57 neutrons now, after combining with the electrons, but also 10 to the 57 neutrinos that are created during the collapse of the iron core. And this burst of neutrinos escapes from the stars, because remember, neutrinos don't interact with much. They'll just go right through the star, carrying away a large amount of energy, about 10 to the 46 joules. Compare 10 to the 46 joules to around 10 to the 44 joules, which will be radiated from the sun over the course of its main sequence lifetime. Lots of energy. So lots of energy leave just as the neutrinos. The core is now a sphere of 2 times 10 to the 57 neutrons that are essentially in free fall. Can anything stop the headlong collapse of the neutrons? Yes. Core collapse can be stopped by neutron degeneracy pressure. So we made neutrons, we lost a bunch of neutrinos, we lost a bunch of energy from the supernova, which, by the way, also cools it down a bit. And we collapsed the neutrons down to where they're degenerate, but you can't collapse it any further because of neutron physics saying neutron degeneracy pressure, at least under these circumstances. The Fermi exclusion principle applies to neutrons as well as to electrons. Degenerate non-relativistic neutrons thus have a pressure. There's a formula for that. And all in all, you basically get the radius of a neutron star to be around 11 kilometers, 10 kilometers, 12 kilometers, something like that. And that radius, it's because of the neutron degeneracy pressure. So hopefully that answers the question for the neutron star being neutrons. There's basically a lot going on. The neutron star is the stellar remnant, but really the process of that core collapse supernova has all the secrets to why we get a neutron star at the end. All the things that happen during the supernova, some of the things leaving, some of the things collapsing, is hello the bears, is leading to this neutron star, okay? Is the black hole itself increasing its radius or only what it's captured? So are you saying why the supermassive black hole gets bigger and bigger? So for something to qualify as a black hole, it has to, you just solve for the radius at which escape velocity would be the speed of light. But yes, as far as a black hole radius goes, at least relativistic and classically, then that is just dependent on its mass, right? So more mass means more radius for sure. Okay? Because we just saw We solved for somebody's black hole radius here. So yes, when a black hole eats more matter and becomes more massive, its radius does go up. Hello, TX Justin. How are you doing? The Bears is saying you educated me tonight. Thank you. Good job. Hi, Pranay. Oh, so let me get back to the question to see if I answered all the parts of it. So hopefully that makes sense. The pretty much the black hole radius is proportional to its mass. Okay? So if a black hole eats more matter and becomes more massive, its radius will also go up. And actually that is also connected with its with its entropy. So entropy of the universe always increases. We were reading about this at one point. Remember, if you were here, basically, it's kind of strange, right? Things falling into a black hole and then just kind of disappearing inside the black hole. We don't know what happens, right? How does that manifest in entropy increasing in the overall universe? Because we know that once something is inside the black hole, past the event horizon, we can't see what happens anymore. That information is kind of lost. But at the same time, we know that every process in the universe should lead to its entropy, overall entropy in the universe, increasing. And turns out that that is kind of respected by black holes in the sense that its event horizon does change. Its radius does get bigger when it eats more things. So in that sense, entropy, that entropy law is followed. We read something like this from A Brief History of Time, in case you want to go back to that live. We had more details about that there. Thank you, Adam, for the question. How is Atlas passing? What's your thoughts on Atlas? Do you mean the particle experiment, or do you mean let me look it up so I understand. Oh, the comet. I got you. So because I come from the particle physics, because I come from a particle physics background, I thought of something else. I thought of the Atlas experiment at the Large Hadron Collider. I don't know much about this comet, actually. So much potential, and she just lets her family down. Are you part of my family, TX Justin? I'm beginning to wonder if you're my cousin. I have many. I have so many cousins. I think TX Justin might be one of them. Hello, brother. So, yeah, I don't know about the comet too much. Extended familia. I don't know about the comet too well, to be honest. Anything else? Let me look over here for a second, and if you have any other remaining questions, last few things, messages, good nights, then put it in the chat. Okay. Thank you all so very much. It's been a great discussion, impromptu. I was a little bit busy today with all my work. I almost didn't go live, but then I was like, you know what? Let me run this and go live. And then I came on, and there were lots of people and lots of good questions today, I thought. So thank you for that. Thank you, Adam. Aw. So nice. So many supportive comments and questions. Number 1, Acacio. Number 2, Adam, for the top fans. Thank you. Okay, so thank you, Mr. Bates. Mr. Bates is saying, I think you're doing a fantastic job, and thank you for your insightful lessons. Yay! I've got questions for you, sir, says Adam. For Justin. Yes. Go ahead. Indeed, go ahead. I thought today was very nifty because we calculated the Schwarzschild radius of Ivan. So that was always a dream of mine. My dream, one of my many dreams, was to calculate the Schwarzschild radius of Ivan on a physics live. And it's been fulfilled tonight. So I'm pretty happy, actually. That's pretty cool, actually. Okay, let me keep on doing my stuff over here, and happy to hang out and address anything else. Hi, Cyprian. Cyprian E8Y. I think TX Justin really wants to do a super chat. TX Justin, transmit Justin, feel free. I don't mind at all if you want to do a super chat. My dream was to hear someone work out Ivan's event horizon point today. Yeah, and it's very tiny, isn't it? He's 185 pounds. 185 pounds. My leg press, my leg press right now at the gym is 165 pounds. Maybe in the next couple weeks, I can leg press an Ivan amount. That's another aspiration of mine, is to leg press 185 pounds after, but only after I calculate the Schwarzschild radius of Ivan, not before. First, calculate the Schwarzschild radius of Ivan, who is 185 pounds. Next, leg press an Ivan amount of mass. So my legs can get stronger and I can carry groceries. Thank you, universe. Thank you for all your help, support, protection, blessings, kindness, and guidance. Thank you. Thank you. Would it make your parents any less disappointed if I did a super chat? They'd be so excited if you did a super chat. Poor Ivan, he'll need a particle accelerator to detect him. True, but also, poor Ivan, if he really wants to become a black hole, we'd have to figure out how to compress him to that level. That's going to be tough. But yeah, Next aspiration is to leg press 185 pounds. Right now, tonight, I was at 165 pounds, which I'm pretty proud of. What's a really dim cosmic object? There are things that are like brown, like not quite black holes, but like compact objects. Remember we talked about machos, massive, compact halo objects. There are actually some dimmer things in the halo. Yes! Thank you. Somebody said a brown dwarf. Mr. Bates, yes. Mr. Bates is saying brown dwarf. There you go. Exactly. Not as dim as Justin for sure. Oh my gosh, sorry. Didn't mean to laugh so obviously. But yes, there are compact massive objects that are not black holes. They can be brown dwarfs. I guess a brown dwarf is a pretty dim white dwarf. So there is more diversity. If you could get beside it, you could touch it without burning yourself. Wow. So Mr. Bates, are you in astronomy? That's so interesting. And your questions and comments have been most delightful. Thank you. As always, thank you everybody for being here and asking and commenting. Adam, Mr. Bates, everybody, thank you so much. Are you studying astronomy, astrophysics, something like that? Scientist. Yay. Thank you, Cyprian. Okay, let me run some more stuff while I hang out, okay? What do you do for work if you can watch till 2:30 a.m.? Oh, are you in Ireland? Oh, it must be early morning for you then, Mr. Bates. Molecular scientist. But in Ireland, if you want to study any science, you have to study all fields of science for 2 years first. Oh, I love it. I don't think I've met too many people from Ireland. I almost went to Ireland actually for my birthday this year because I've never been. That's awesome. Are you from Ireland or are you there just for your schooling or for work? That's so cool. I'm from here. Okay. Nice to meet you. Please do like, share, subscribe. We have more videos, shorts, all of that stuff coming out as well. So hopefully you enjoy. It's coming up on Friday. Okay. Took care of that. Yes, we're gonna do a birthday special live, Aman. With Baji and everything. For sure. No, I just had a moment. So I hit him. That's all. I mean, I think he goes off every time pretty much. I just hadn't had a chance yet to do something about it. Family, no. Everyone is busy. So, but I'll see my friends. Let's see. Jorge! Trolls are a good sign your stream is doing well. Thank you! Oh, that's most encouraging. Thank you so much. It has been so rainy indeed. It's been a very rainy couple of days in Boston. It's like bigger planets, they pick up more space junk. You're so right, Adam. We're so successful now. I even had to block a few people who were being so disruptive. Yes, there are kitty cats about. You'll see some kitty cats in the videos, Mr. Bates. Yes, indeed. Bigger planets, they pick up more space junk. I love that. I love it. I love it. I love it. I do love it. Okay, you know what? I think I need to change this part. You know what? Let me take that out and rerun this. Okay, I see. Huh. What time are you going to bed? I'm getting ready for work. Soon, soon here. Pretty much in a few minutes. We'll wrap it up. Where are you joining from, Jorge? Are you in Europe? I'm looking at my code. I'm doing a study with me at this point. I was talking a lot, but I have to fix something and start running it. And then I will go to bed. Ooh, you're in Providence? Where do you work? You're already going to work? Wow. Are you in the medical field? Hmm. Cool job, bro. Yes. Okay. I am wondering. Good night, Adam. Thank you. Thank you so much. just don't understand this. To be totally honest. Yeah, I am. I am troubleshooting something. I don't get it. I don't get it. I'm not. Let's give this a shot. Let's give it a shot. I have to try it in the morning. Yeah. Anyways, yeah, I'm trying something. Thanks for joining. That signed. Thank you. Thank you, Cyprian. Thank you. Great meeting you. See you next time. We go live a lot. See you next time, Mr. Bates. Sing a childhood song. It would help you think. I'm trying something. And if that doesn't fix it, then I will just have to try tomorrow. At this point. Okay. Yeah. I have quite a lot of work tomorrow, which is fine. Yeah, I should be live at least a couple more times this week, so watch out for that. If you're subscribed, hopefully you'll get the notification when I'm going live, and hope to see you then. Excuse me. Okay. I am good for now. Thank you, Adam. Thank you, thank you, thank you. Oh, this is so heavy. Adam is so supportive. Thank you. That should not take too long. Okay. Ugh. Can we get 40 likes? I never shared the live today. Oh. Who is this now? It says 40 already. Oh, thank you. I don't see 40 yet, but thank you. Gosh. Apparently, I'm even more famous than I thought, Adam, because now even some kind of scammers are joining the live. Oh, goodness gracious me. Thank you, Mr. Scammer, for joining. Okay. I see. Alright. I'm gonna do this thing tomorrow. Okay. 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 Alright. Well, well, well. I must say goodnight now. I do have to finish up some stuff and then go to bed. I have enjoyed speaking with you all very, very much and reading all your comments and messages and everything like that and getting your support. Thank you so very much. Have a lovely night, my dear, says Cyprian. Good night indeed. Mwah. Good night. Sleep tight. I love you, miss you, and I hope to see you very, very soon. Cyprian, Adam, Mr. Bates, everyone, Steven, everyone, thank you so much. Acacio, thank you so much, very, very much indeed. See you next time. See you very soon, actually, this week, hopefully, very, very soon. Thank you, universe, and a good night and sleep tight. Mwah. Love you, miss you.